Rolling.
Rolling. So at the moment, our pendulum is just hanging here. What do we call this position where it just hangs?
Equilibrium.
Equilibrium position. And at the moment, what forces have we got acting?
None. No gravity.
No net force, but we got gravity's going down.
Oh yeah.
But it's not falling.
Tension.
So the tension force of the strings pulling it up. And we can displace it from that equilibrium position and let it go. And what we notice is that it swings back and forth in periodic, repeated motion. We call it simple harmonic motion. Where's it going the fastest? At the equilibrium. So as it passes through the equilibrium position, where the displacement is zero and where the acceleration is zero, that's where it goes the fastest. What about the opposite? Where does it stop?
The peak.
Yeah, out at like the amplitude point, at the maximum displacement, it stops. And what do we know about the acceleration at that point? It's maximum, and it's going that way. What way have we displaced it? That way. And so that's like our fundamental rule for simple harmonic motion, is that acceleration depends on displacement, and it's in the opposite direction to displacement. So if we displace it to the left, it accelerates. To the right. And the further we displace it, the more rapidly it's going to accelerate. Displace it further, more rapid acceleration, higher speed. So that's, in a nutshell, that's simple harmonic motion. Let's write some of that down, shall we? That's what we're going to learn, basically, is how to calculate the acceleration or displacement or velocity at any different point in the motion, which is quite complicated because it's constantly changing. Everything's constantly changing. Like the displacement's changing, the speed's changing, the acceleration's all changing. So it's hard to find something to hold on to that stays the same. That's the way we're going to try and solve this, is find something that stays the same in that motion. Anyone got ideas about what stays the same? Length stays the same. The mass does stay the same. What else stays the same in that motion though? Gravity. Period. Stays constant.
What's supposed to?
Supposed to. As long as we don't swing it too far. And so you guys are going to see this called SHM. Like in real life people call it SHM. They don't say simple harmonic motion because it just takes too long. So SHM. So the A is acceleration, ms minus 2, and the y is displacement, which is a little bit annoying because we kind of got used to and comfortable with x being displacement, but y can be displacement from now on. What's the minus sign mean? What's that telling us? Direction. What about it?
It's opposite in displacement.
So the acceleration and the displacement are in opposite directions. And then the k is just some number that makes it work, and we're going to come back and give that like a value. It's going to work out in our maths, but just at the moment it's just some number. It's like A is proportional to displacement, and there's some number in there, like a proportionality constant that makes it true. We're not going to worry about what that number is right now.
Is it better for our learning than worry about it?
Yeah. Definitely. Oh no, you should worry about it. What's good for your learning is to be like frustrated and annoyed and like uncomfortable.
Yes.
Yeah.
And then like have the answer revealed to you, and it'll be like, it'll really stick.
I think it's good for your amusements.
They say that like 5 minutes of discomfort is really good for learning.
Yeah, no, well, yeah, that makes sense.
Makes sense.
You know how much more like 5 minutes of a question?
Like when you do a do now, there's a question you don't, like you can't quite get, and you like spend quite a bit of time trying to work it out. And then you see like how to do it.
Yeah.
Like more likely to remember than if I just showed you.
No, that makes sense.
That's my theory. So like a pendulum's a really good example of simple harmonic motion, but we're not just doing a simple pendulum. It's a really good example, but it's also a really annoying example to solve. So it's nice to think about because it's really obvious that the equilibrium position is in the centre, and that at that equilibrium position, we know that the acceleration is 0, the velocity is maximum, and the displacement is 0. And at each of these like amplitude positions here, what do we know about those values?
A is max.
A is max.
And Y.
V is 0. Y is max.
Kind of put a negative sign in there,
Hey.
because you kind of
Negative
displace it
maximum.
backwards and it's trying to accelerate forwards. And over here then,
Same.
Same except positive max. On the. You said same.
So do you just pick a side to be negative A?
no, left is negative, right is positive.
Yeah.
Yeah, but when you were standing on that side, it was different to when we were on this side, right?
When I was on,
When you were on that side of the pendulum looking at it, and we were on this side of the pendulum looking at it.
oh, perspective.
Yeah.
Played into it, yeah. But now that we're running it down, we're both seeing it from the same perspective.
Alright, seems legit.
Just go with it, shall we?
Yeah.